Welcome. So today's going to be an exciting, potentially maybe a little bit more expensive day as we start to explore vertically scaling our EC2 instance for our web tier. In the last video, we talked about kind of squeezing as much from our application or our web tier as we possibly can. So we talked about setting up caching. For Laravel, we talked about using PHP Artisan Optimize. And one of the things that I didn't talk about last time that we should is PHP Opcache. You would definitely want to have that on. It makes a big difference. But in this video, we're going to leave all that a constant, and we're going to start to explore vertically scaling. So choosing different EC2 instances, going from the T2 Micro to kind of maybe a T2 2XL. So instead of having one virtual CPU core, now I have 8, and see what difference that makes in our application. In a follow-up video, we're going to do the same exploration, but we're going to look at horizontally scaling our web tier. As always, if you're enjoying content like this and you want to see more, like and subscribe. Because today is potentially going to be expensive as we start to transition from these non-free tier EC2 instances to some rather large ones, I want to have a process in place so we can kind of get in and get our testing done and then shut that instance down. All right, but let's take a look at where we're at first of all. So we've had a number of videos in this series ranging from our initial monolithic deployment to kind of getting us positioned to where we are today, where we have this multi-tier application. We also talked about in there DevOps and having infrastructure as code and a CI/CD pipeline. So we covered a lot of different areas. And we also talked about scaling the other tiers that we have in our application. But today we're talking about scaling this web tier. We have one video in this web tier where we kind of explored what are some of the levers that we have to pull to kind of do that scaling, and what's kind of the theoretical values that you want to set in there. We're going to recap that video, and then we're going to dive into kind of actually doing the vertical scaling and testing those EC2 instances. Before we move on though, here's some kind of real world examples of, some of the request response monitoring that's out there. And I want to bring in both of these here. So you can, for example, see this is from OpenStreetMap. They're hitting say 400 requests per second. And down here you can see kind of the requests per second for, the Wikimedia sites. So they're looking at 150,000 requests per second. And what we're talking today is we're going to do some vertical scaling of our Laravel application, and hopefully we can get to this couple hundred requests per second. So that feels like it should be pretty easy to get to, but getting to 150,000 requests per second, that takes a lot of fine tuning and probably some horizontal scaling in there also. So we're not going to get to that level probably at all during this series, but we'll explore some horizontal scaling in the next video. And just quickly recap where we're at. We have a Laravel application. These are kind of the tiers that we have and some of the applications that we're using. So we're using Nginx, we have PHP-FPM, Redis cache, we're using MySQL for the database. Initially we deployed this in a monolithic deployment, but we are no longer there. We have this 4-tier deployment, and we have a web tier, a database tier, a caching tier, and the workers tier. And what we want to focus in on today is just this web tier. How can we vertically scale this web tier? And just to kind of get everybody on the same page, here's our Amazon infrastructure that we have. We have 2 availability zones. We have the caching tier and the database tier. We're using Elasticache and Amazon RDS, and those are deployed across multiple availability zones for our application. We have one worker tier that's in a private subnet, and we have our web tier. It's a single web tier right now, and that's the instance we're looking at scaling. That's in one public subnet. So if we take one request and response and we look at what that impacts, a request comes in, it goes through Nginx proxies it to the PHP-FPM service, where then the PHP is executed. So now we're into our Laravel framework, and depending on the request and what resources that request has to access, it may hit the Redis cache, it may not, it may hit the MySQL database, it may not. And then finally, Laravel will take that content that it got from the data stores, Redis or MySQL, package it up into some view, so it'll kind of take the Blade template and compile it, and then it'll return that HTML back up the stack through PHP-FPM to Nginx. I want to touch base a little bit on testing, because we could really, depending upon what we test, we could really skew our results, and we could look amazing. For example, if we were just to put a raw HTML page, a test.html, that would bypass PHP altogether. And we would get amazing request response results. Their speed would be really fast, and we'd probably hit thousands of responses per second. But there's no PHP involvement here. So that kind of test, yeah, we look amazing, but it's not really testing our application. We could also have kind of like a ping test where maybe we have a special route in Laravel and just returns the text Pong. So it doesn't really get into the blade view at all. So depending on how you set up that ping route, it may still start up a session. So it could incorporate some Redis cache in there, but we're still going to get pretty quick results because it's not really doing much besides just kind of returning that text response of Pong. The worst results would be if I hit a page, I don't know, I just put /data in here just to kind of give you a visual, but that route would go and query the database. It would incorporate the session cache, and then it would also take into account all of that data that you grab from the database and create a view. This would bring us the worst results if we were kind of testing our request responses, because that would be definitely the slowest. But I think kind of the practical test is something in between. And I'm just going to hit our login page. And I know that will return a blade view. It'll also hit the session cache. So it's going to hit some of Redis, but it's not going to incorporate the MySQL performance at all. And the reasoning for this is because I'm really interested in tuning this stack here. So interested in tuning Nginx and PHP-FPM. And if we have to, we'll take a look at the Laravel logs and see if there's any errors happening in there. But that's kind of where I want to look at tuning. Nginx and PHP-FPM. I'll focus in my tuning efforts there, and I don't want to incorporate MySQL or Redis if I have to. I'm not saying that MySQL isn't an important part of our application. Of course it is. We've already talked about scaling MySQL. We put it into an RDS instance, has multiple availability zones, and that is already set up on its own to be independently scaled. What we want to focus in on this session is just scaling our web tier, which is the Nginx FPM Laravel integration, how those pieces are integrated and how that request response is handled in there. So that's what we really want to focus in on. So I think that this login route is probably a very practical test. The other thing I want to talk about is what are we expected as a results. So over time, what we're going to do is we're going to increase our requests per second over time. So, we're going to start off kind of at 0, and then we're going to increase this up to some number, say like 3,000 requests per second. And then what we're expecting from our application is, first of all, I'm expecting 0 errors. If all of a sudden I hit a spot where I get some requests per second threshold, and if everything turns into an error because maybe Nginx is out of file handles or PHP-FPM can't handle the response load, then I've pushed that system too far. So I want to make sure that I have 0 errors. And so again, under our tests, we control the request per second, and then what we're going to measure is the response time, and that'll be in seconds. So for example, typically it's sub-second to load that login page. And what I want to see is what that response time does as we load our system with more and more requests per second. Intuitively, I'm thinking that this is going to be a linear response time. And as we go and add more and more requests, it's going to take longer and longer for the system to handle that request. And then obviously, as the response time increases, there's kind of this threshold that I don't want the user experience to get above that threshold. And whether this is 1 second or 5 seconds or 10 seconds, it kind of depends upon the application. But most people, when they visit a website, we're typically sub-second on that response time. And even though when we're surging our request per second up and we reach this threshold, it doesn't mean that EC2 instance isn't a good instance still. It just means that if we ever hit a load of kind of that magnitude, the responses are still making it back to the user. They're just making it there slower. And so maybe, in certain situations where there's like a surge, we can handle the surge, that EC2 instance can handle it, and then it gets back down to kind of acceptable response times. All right, in the last video, we kind of dove into, what are the handles that we can pull. For Nginx configuration, it's in the etc Nginx conf file. Inside that conf file, there's a few things that we're going to be working with this time. We talked about last time other things, for example, making sure that gzip compression is on. And we talked about a few other possibilities in that last episode also, so go back and visit that. But in this video, we're going to really talk about 3 kind of variables. One is the worker processes, and that defines the total number of processes that Nginx has run at any time. The recommendation that I saw for this is we set it to the number of CPUs. We're going to start off with just 1 since we're on the T2 micro. Then there's another variable called worker connections, and that's the number of simultaneous connections that each worker process can handle. So if you have 1 worker process, this is the number of connections it can handle. Every connection needs a file handle to be able to kind of do its job. By default, the limit on file handles is set to 1024. So the maximum number of connections, if you leave everything the same, you should set that to around 1024. But that number of open files for each worker process is configurable. So there's another variable called worker_rlimit_no_file. You can increase that limit to handle more connections. That's going to be an important variable that we're going to look into also. On the PHP-FPM configuration side, again, this is under etc/php/8.3 because I have version 8.3 installed. In the FPM directory, there's a pool.d directory. Inside that, you have a comp file for every pool you have defined. And then one of my comp files is called demo_1 comp. And that's the one that we're going to be hitting for our Laravel application. And there's 3 variables in here that we're really going to focus in on. So first of all, the process manager can be set to one of 3 values: static, dynamic, or on demand. I should say demand instead of on demand. And which you set this to really depends on your application. You know, I talked about in the last video how I have a number of different kind of pools. I have demo_1, maybe demo_2, and I can easily add a 3 or 4. So in the previous video, I reasoned that I was leaning towards dynamic. For this testing purposes though, I'm going to go with static. It's the fastest modality for this configuration. And the reason that is because it automatically spawns up the max number of children, and those are spawned up right away. And then they will respawn after that certain number of max requests, which is configured down here below. So max children is the maximum number of child processes that will be created. There is a formula for this, and last time we explored that formula, and it's really the available RAM. So the total number of RAM, the total amount of RAM, subtract away everything that's being used by other processes, and then that's the available RAM, and you divide that by the amount of RAM per kind of child process. For the T2 micro, we computed this last time and it was around 15. So that's the value we're going to start at, is 15. The third variable is this max_requests. That's the number of requests that can happen on a certain child process before it gets respawned. And this is useful if you have an application where you suspect you have memory leaks. And it might not even be in your code. Maybe it's in a third-party library that you pulled in using Composer or something, and there's a memory leak in there. And so what happens is this will respawn those child processes and help kind of circumvent that memory leak. And by default, we're just setting this to 10,000. Just to kind of set the stage for testing, you know, we have this black box. We're going to assume that that's our stack from Nginx, PHP, Laravel, the Redis and MySQL is all in there. So that's our device under test, and it's a black box. And then what we have is we're going to have some device that we're going to use to test that black box. And that could be my own personal computer. For example, I might use Apache Workbench and hit a URL and tell it to go and do a certain number of requests, but that's the device that we're using to actually do the test. And then obviously there's some networking between these 2 devices. And we want to be careful that we understand what's the property of a device under test versus what's the properties of this networking or this testing device. You know, as an example, when I was doing some Apple benchmark testing locally, so I was using my Mac to run Apple benchmark, I could easily saturate my local computer or my local network, and that saturation turned up to be kind of artifacts on, you know, the number of requests per second that I could actually get from this device under test. And I discovered that because as I started to increase the instance sizes, I was expecting the number of requests per second to kind of go up, and it kind of flatlined around 350 requests per second. And it didn't matter if I added more CPU, more RAM, or whatever I tried. I couldn't kind of broach that 350 requests per second. And the reason that was is because I was saturating my local infrastructure, my device, my testing device, or my network. You know, I'm not even really sure where it is, but I kind of had a suspicion that was what's going on. And so I switched back to using loader.io, which totally makes more sense to me. So to minimize these artifacts, we should kind of parallelize our testing devices so that we're using, you know, many different testing devices and many different networks, so that any kind of limit that's part of our testing device or that network doesn't really impact our test results. At a high level, here's our testing process then. So we are going to update the Amazon EC2 instance to whatever type that we want to test. Maybe we start off with T2 Micro, and then at some point we're going to make it to T2 2XL. And at some point we'll dive into the other, you know, kind of instances that AWS has available. We're going to use loader.io to do kind of a linear ramp up of the number of requests per second. And then what we're going to do is we're going to look at those results. And when we look at those results, we have that expectation of already 0 errors. If I see that I have errors, I need to dig into my logs. I'll probably dig into my logs regardless, just to make sure that there's nothing happening that I'm not seeing in the results. And also any deviation from my expected results. So, if my response time, it's not linear, but maybe it kind of starts to hook up and it starts to increase dramatically, then I need to kind of dive into the logs and figure out why that's happening. And if I find a root cause of why maybe the deviations are happening, then I would fix those and rerun the test. Otherwise, I'm going to update the configuration files, Nginx and PHP-FPM, and then I'm going to repeat those steps over and over again until we maximize kind of our response times. Okay, so that's the kind of upfront. Let's talk about it. Now let's get into the lab and let's actually kind of do this. We'll log into our servers and we'll start some of this process. Okay, so we've kind of gone over the basics, and what I put together is a game plan that I can go step by step through and get through this in a kind of an efficient and as quickly as I can. So first of all, I went through all the AWS EC2 instance types, and I started with general purpose. We're starting with the T2 Micro, which is right here. You can see that the T2 series, you can scale this up to maybe a 2XL, which has 8 virtual CPUs and 32 megabytes or gigabytes of RAM there. Some of the differences that we'll see as we kind of go along these instance types is we're going to see network performance differences, and we're also going to see storage performance differences. And what I'm going to try to do is I'm going to try to pick 8 virtual CPUs in a bunch of different kind of instance types and see how they perform against each other. So I have this spreadsheet that I've already put together. I'm going to start with the T2 Micro, and then I'm going to go to T2 2XL. And that has 8 virtual CPUs and 32 megabytes of RAM. And then I'm going to go to the M7i 2XL. And again, everything has 8 virtual CPUs. They do differ a little bit sometimes on the RAM. So for example, the T2 and the M7i, they both have 32 megabytes, but the C7i only has 16 megabytes. And this is kind of a compute optimized instance where they're kind of leaning more towards CPU than they are RAM. Under the hood, most of these use the same kind of generation of processors. So it'll be interesting when I compare these to see what the numbers turn out to be. So given those initial values, number of CPUs and total RAM, I used the same formulas that we had the last time. So the number of worker processes for Nginx is equal to the number of CPUs. So that's always going to be the number of CPUs. This R limit, this is the number of file handles that Nginx can have open at any one time. I've already done some kind of initial probing. We do run out of file handles pretty quickly. The default value, which was 1024, I quickly kind of consume all those file handles and we start to get Nginx errors. And I did capture, for example, here's one here where we had an Nginx error with too many open files. And that's kind of what it looks like in the Nginx error logs. And because of that, and also from looking around and getting input from various different sources, I set this to a number like 20,000. So you're going to see that 20,000 mark here all the time. The number of worker connections, I also read that you really require 2 files or 2 file handles per connection. So I set this to 1/2 of this number. So it's at 10,000. For PHP, I'm always going to use the static mode. The other 2 modes are dynamic and on-demand. Dynamic and on-demand are both slower, so we're just going to stick with static and see what our test results look like. And then I computed the max number of children. So this computation is the total number of RAM, which is given by our instance type. So for T2 Micro, it's 1024, minus the used RAM. And I kind of measured the used RAM in the T2 Micro, and it was about 400 megabytes. And so this is the amount of RAM that everything else in the system's using. So, the actual Ubuntu itself, Nginx is in there, anything essentially besides PHP-FPM, 400 megabytes, carving that off. And you can see all the way down through, I'm just carving off that same amount. I'm not expecting that number to increase. I don't think there's any reason why all the other resources are going to grab more memory. So I'm just going to keep that as a constant 400. And then the other number we're going to hear is the amount of RAM per child FPM process. And I measured that, and I measured it once, it was around 60. I measured it again, it was around 80. And I think just depending upon when you measure it, it kind of does an average of kind of the most recent history. That number will vary. I took a conservative approach and I set this to 100. So to compute 6.24, I took 1024 minus the used RAM. So that gives me roughly about 600 megabytes left over, and divided by 600 by 100, and I end up with around 6. And then finally, the PHP-FPM max number of requests before a child process is respawned, I set that to 10,000. So this is my plan here. So I'm going to go through these instance types. I'm going to set them up initially with these initial values, and that'll be kind of our initial set point. And then what we're going to do is, based upon that set point, we're going to kind of tweak parameters around that set point, and just to see if that performance can be optimized anymore. Okay, and just to kind of orient us, I got my AWS EC2 panel up. I'm already running the T2 micro. It says initializing, but it should be already initialized. And we're set and ready to do the T2 micro tests. And then if you recall, I have a number of endpoints. We have kind of just the regular endpoint here. This hits the database. I'm not going to use this in testing. We have a login endpoint, which doesn't really hit the database. It does hit the Redis cache. It starts up a session. There is some kind of view, some blade templating kind of going on here. There's another endpoint I could use, which is the op cache for PHP. Op cache is turned on and it is running. From here, I'm able to kind of monitor it and see if the cache is full and if I need to adjust any parameters with the op cache. I do have a ping route. I'm not using this because I think that's cheating a little bit. It's not really going through all of the Laravel stack that a normal route would go through. So we're not going to use this. And then as previously discussed, I'm going to use loader IO for the testing. And what I've set up is I've set this up so the route is the login route. And I'm going to ramp clients up from 0 to 3,000 clients per second. It's going to be a linear ramp up like we talked about. And then what we're expecting is some kind of linear response. And so there's my test plan. So what I'm going to do is I'm going to run through all these instance types. I'm going to try to get through the ones that aren't free as quickly as I can. All right, up first is the T2 micro. And the initial computation, I have one Nginx worker process, and I have about 6 PHP-FPM child processes. So here's the T2 micro slide. I've got that in here, 1 and 6, and we're ready to do some testing. All right, I'm already logged into the instance. Let's check first our configuration for Nginx here. And let's back this down to 1. And again, here's that 20,000, here's the 10,000. So that's good for that. And notice I'm stopping and then restarting. I read some places where if you just kind of reload it, it doesn't really happen right away. It takes some time to kind of get those worker processes. I'm not really sure if that's true, but it doesn't take me much more time to just stop and then start. So that's what I'm doing with Nginx. And here's our PHP-FPM pool. And for the PM, see we're at the static here. And here we're going to set the max children to our value of 6. And then the other value down here that we wanted to look at was the max request is set to 10,000 right now. And we'll restart PHP-FPM. Okay, so at this point we should be ready to run this loader IO test. So we're going to switch back over to loader IO. And again, my test is already set up with our login. We are going to execute this test. And you see I've already done a number of, I've been probing this for a little while. So I kind of did that to get my initial game plan set. But let's go ahead and run a test, a fresh one. So, okay, so our first test is completed. And what you can see here on loader.io is this green line is the number of clients per second. And so that ramps from 0 up to 3,000, which is how we've got it configured. That's our kind of input stimulus to our device under test. And then what we're measuring in as a response is we're measuring the blue line, which is the average kind of response time. So how long does that response taken? Okay, and so the numbers that I want to collect here is we're going to collect this average. And I'm going to save that for every single test. And we're also going to collect this maximum value here. And you can see that I had a number computed. It's 59 client requests per second. So clients per second, so CPS per second. And what this number is really kind of the slope of these two kind of lines combined together. And so to compute that, just to show you what I'm doing to compute that, and after this, we won't talk about this every single time, but this is going to be equal to that 3,000 requests per second times 1,000. We'll talk about why 1,000 in a second, divided by this maximum number, which is 50768. Okay, And so the reason the 1,000 is here is this is in milliseconds. So I'm going to get that into seconds. And so really I'm taking this number divided by 1,000, which is the same thing as multiplying the top by 1,000. So I got 3,000 times 1,000 divided by that number. And that is this 59 number here that you can see. So that's how that number is being computed. And then let's just talk about the meaning and the reason why I'm kind of grabbing that as a metric here. If we look at our chart, our graph over here, this blue line came up to 50,000 milliseconds. So when I'm requesting 3,000 clients per second, the average response time the person's waiting on the request response is about 50 seconds. So imagine now that instead of 50,000, we're all the way down here, say below 500 milliseconds, say around 500 milliseconds. So that's a better situation, right? So clients are only waiting like 500 milliseconds per page. So let's go back over to our formula and let's see what the number would look like. So instead of putting 500 there, or 50,000, if I put 500, you can see that the CPS per second, or the slope, is going up 6,000. So this metric, as it gets bigger, that means that it's a better performing system, or we've optimized it more or less. So that's one of the metrics we're going to look at as we start to tweak parameters over here. So the first thing I'm going to do is I'm just going to make some small changes. And first thing I want to test is the Nginx performance. And I want to move this to, instead of 1, let's bump it up to, say, 3 and see if it makes any difference in our test results. So that'll be our first kind of iteration on this manually optimizing the performance here. So we're going to switch the number of worker processes to 3. Stop it. Start it. And then we will run our test again. So it's completed. I do like to refresh the page once because sometimes these numbers slightly changed. Didn't quite get the last one. All right, so we're going to take the average and we'll put that over there. We'll take the max and we'll put it right here. So, and just as a comparison, you know, we're pretty much staying, this average response time is the same and the max response time is pretty much the same. The metric, that slope, is slightly improved, so it didn't really make a big difference. I would say it's kind of a null impact here. So we're going to go back to 1. And the next thing I want to look at is this max children. I'm going to start to play with this number. So instead of 10, or instead of 6, let's drop this to, you know, maybe 1, just to see what the impact of having only one child process for PHP-FPM is. So we'll get in here, we'll make our change. Max children's 1. And always have to remember to restart these services so they take effect. And we should be ready to go. And we're going to kick off another test. And while that's running, let's do a quick look here at glances. Almost always, what I saw when I was doing some initial testing, when we run the test, the CPU is going to max out. By default, PHP-FPM and Nginx are going to take up all of the resources on that machine and try to deliver the best request response time. So almost always it's going to max out. When we get these larger instances, very little did I ever see kind of the memory kind of max out. Even in the T2 micro, you can see we're only using 60% of the memory. All right, so we're just going to refresh. We'll kind of do our process. We're going to grab the average number, plop it in, grab the maximum number, and we'll plop that in here. And so you can see the thing that we changed is, we went from back to this initial one, which is we're going to compare it up to this top line. Our average response time went up a couple hundred milliseconds about. So that's kind of a big change, 200 milliseconds, bigger-ish, let's say. Our max went up about a second. And you can see our slope number, that went down. So we headed in the wrong direction here. So let's go ahead and do it one more time. And let's see if we can improve it by increasing it from 6. Let's go up to, say, 10. Let's see what that number does for us. And we kick off our test. So you get the idea. It's a lot of repetition, starting off with the formulas to kind of give us a default spot. And then what we're doing is we're just looking to see a little bit on every side of those variables just to see, if we can optimize it better than what that set point is. While it's running, let's go ahead and look at glances again. We have more PHP-FPM processes. So are we using more memory? And if I remember right, it was in the 50s before. Now it's 65. So we are kind of using more memory. Looks like the test is completed. We're just going to refresh. I'm going to grab the numbers. And you can see in this case, 10, it actually is performing worse, right? So from the top line 6 to 10, we are over a second. We're about a second, maybe half a second slower, 600 milliseconds slower. And our maximum is increased by like about 2 seconds, it looks like. And our slope number is decreased. So far, we are looking at kind of the sweet spot is right where we had computed it for the T2 Micro, which was about 6 PHP-FPM max children and 1 Nginx worker process. All right, the next thing I want to do is I'm going to run pretty much line 1 again, but I'm going to change this max request. If you remember right, this is kind of how much churn our PHP-FPM processes are going to have. PHP-FPM starts up, say, 6 max children, and then once they handle, say, 10,000 requests each, it kills those children off and then respawns them. What I'm going to do is I'm going to bump this down, and I'm going to go to a number that we probably would never have in production, because I kind of want to see that number is having some kind of impact. So I'm going to say after every 100 requests, we're going to respawn. Let's just see how much overhead that respawn and what the impact to our numbers are. So here's our max request. Right now it's set to 10,000. We're going to bump this down to 100. Restart PHP-FPM, and let's kick off the test. And just visually, I don't know if this wagging around is kind of because of what we just caused, but it does look not as linear. And like there's sometimes where it's a little quicker, and then it's a little slower, a little quicker. So it's got a little wave in it as it's going up. Let's look at glances real quick. 64% of the memory again. 100% of the CPU. I forgot to switch this back, so we're actually running this test right now. We're running max children 10 and 100, so that's kind of the test we're running. And it looks like the test is completed. Let's go and pull the max over. And let's pull over this number. All right, so the comparison is really between these two lines right here. So this row and that row. The only thing I changed is I changed the max request from 10,000 down to 100. So you can see that the average response time is a little slower. It's a couple hundred milliseconds slower, and same thing with the max response time. So a couple hundred milliseconds, maybe that's not bad, but what we're going to do is we're just going to go ahead and keep this at 10,000 throughout all the rest of the tests for the rest of the kind of instances, and we'll just keep it as a constant. All right, so for this T2 Micro, the space that we're kind of exploring around, I think if I went down to 1, it didn't get better. I went up to 10, it didn't get better. I'm not going to twiddle around with kind of the incremental like 5 or 7. What I would rather do is put my efforts over to kind of the other larger instances. So for now, we're going to call row 1 our winner, and I'm just going to mark this as a green cell. That way we can clearly see that. And I don't know why these are green, but we're going to get rid of those. So for the T2 Micro, that's our kind of configuration that we'd run with if this was our production machine or a dev environment. We're going to try to go with the formula, and 1 Nginx worker process, 6 max children for PHP-FPM. All right, so far we've got the T2 Micro tested. Up next, we're going to test this T2 2XL, and we're going to put our data in this one. And I've already transferred over our initial settings, but what we have to do now is convert our T2 Micro instance over to this T2 2XL instance. we can do that in our EC2 panel. I'm going to record this process once, and then after that, whenever I change an instance, you can imagine that I did this in the background again. So the first thing we do is we're going to select the web, and we're going to set our state to stop. We want to ask it to stop first. This doesn't take too long here, but I usually just hit refresh, and you can see it says stopping, and I would say within about 30 seconds or so, it'll say it's in its stopped state. So you can see right now it's in stop state. And then under the actions menu, under instance settings, we are going to, it's not quite ready for me. Oh, I didn't have it selected. All right, so you got to select it again. And then under instance settings, we are going to go to instance type. And right now you can see it's T2 micro. And then, I was going to grab this price too, because I don't have that on my spreadsheet yet for the T2 micro. That's our number. And what we're going to do is we're going to bump this up to T2 2XL, which is right there. And you can see it does a nice comparison for you. So I'm going to go ahead and grab this number for our cost difference. And we're at 8 CPUs and 32 megabytes of RAM, which is what we already see here. So the only thing that we have to do then is click apply. And as long as you're within the same kind of architecture, so here we're kind of going from Intel-based architecture to Intel-based architecture, it'll be able to kind of do this kind of transformation for you. If I try to switch this to an ARM-based architecture, it will not be able to do that. So we're going to click apply. And then you can see it's still stopping out. It says T2 2XL here. And the next thing we're going to do is we're going to restart our instance. And this will take a little bit of time as it restarts back up. And we'll just keep kind of refreshing here. And I'm waiting for it to get its domain name here. So the DNS name, this is the public DNS. And if you recall, we are testing with this route. So we have to have our route updated in Route 53. So we have this hosted zone, and that's called Nextler, and there was this record that we had set earlier. And this previously was our T2 micro instance, but now we're going to update this to the T2 2XL instance. And that domain propagation, because we're already kind of using Route 53 for our DNS, that change of that record happens pretty quickly. So you can see it says 60 seconds here, but in my experience, it's already done, right? So it happened within seconds here. So I'm already refreshing. I'm on that new server. We're going to go back to that new server. It says they're all running. This one says it's still initializing, but we can still connect into it. So this is our public IP address. We're going to go back to our terminal window. We've got disconnected, you can see, but I'm just going to reconnect using our new IP address. And you can see how many times I've done this. There's 12 additional names omitted. I've been kind of probing this quite a bit with different things. So you hit yes to the new IP address, and now we're in that instance. And while it's still kind of getting itself all set up, I want to make sure that we set up our first test. So Nginx worker process is set to 8, and then we have 323 PHP-FPM children. Just make sure all the variables, so we got static, and the number I want is 323 based upon our computation. And let's make sure this is set back to 10,000. All right, so we should be all set up. And when I was in Nginx, I did notice that I failed to switch back from 3 to 1. So these tests were really running Nginx at 3 worker processes. Again, from 1 to 3, it didn't really make too much difference here. We're talking, it improved at 60 milliseconds, and up here it was a little faster. So not much improvement, but a little bit better with running at 3. Okay, so we're all configured up here, and we're going to run the same thing. So we're going to go back to our loader.io. Oh, let's go back here. I want to make sure that this is, it still says it's initializing, but sometimes it doesn't update right away. So now we're all set to go. All right, loader.io. We're running that same test. Ramp up from 0 to 3,000. Let's see what our numbers turn out to be. It's our initial tests. Okay, so we have a result. So I'm going to go ahead and copy these numbers over to our spreadsheet. All right, if we just switch back and forth real quick, you can see this T2 2XL is definitely faster than the T2 Micro. So our max response time was around 27 seconds here, and that is kind of about around half of what it was for the T2 Micro. So the 2XL, given additional CPUs and additional RAM, this definitely is helping out. Our slope number is 111, which is improved, so that's better than the R59. All right, so our next goal is to kind of tweak these numbers a little bit, see if we can, try to find an optimal performance area. So right now we're at 323 children. I noticed that when I changed the worker process before from 1 to 3, it didn't really make much difference. So I'm just going to leave this at 8 throughout of all of our tests. And the next test we're going to run will be something where we change PHP-FPM, the max children. And we're already at 323, so let's go ahead and bump this up to maybe 400, and let's see what that number looks like. So we'll kick this test off again. And while this one's running, I don't know if it was apparent, but at 3,000 requests per second, even our T2 Micro, it had a reply. It wasn't airing out, and we were getting a response. Yeah, the response was almost 60 seconds later. And I think 60 seconds is one of the timeouts that's kind of by default for either Nginx or PHP-FPM. So we are about ready to hit that timeout there. And obviously a 60-second response time, isn't even close to something that you would want a user to have to wait through. So can you imagine every response takes 60 seconds? All right, so this test is completed. Let's go ahead and take our numbers over. All right, so by going from 323 to 400, we upped our number like 0.3 or something like that, and our response times, our milliseconds, our average kind of increased a little bit, but our maximum kind of decreased a little bit. So this is kind of a wash. It really was a wash there. Before we talk about our next kind of point that we're going to test here, one of the tabs that I haven't shown yet is this details tab. When I was doing my initial probing, I used this a lot because I wanted to make sure that there weren't any errors in the system. So if there's 400 or 500 errors or timeouts, I would see them here. So if I go back far enough, this is a test I did on June 2nd, and I ran this on around 11:09. This was a ramp up test from 0 to 1,000, and you can see that this is linear in this region, and then all of a sudden it bumped up to kind of this type of thing. When you see this big jump like that, that's an indicator that there's something that's happening. And then when I go to the details page, you can see what happened here. I was getting successful replies, and then all of a sudden down here I was getting these replies here, which are the 500 responses. And because of this initial probing, it's really why I set this kind of max file number to like 20,000. Was my initial probing led me to that was an issue, and so I fixed that issue. And just to be fully transparent on some of the other issues I found when I was doing my initial probing, I did run into, obviously I ran into this too many open files. I set that number to 20,000. I didn't update my worker connections at that time. I just let them sit, and then I ran out of that. We didn't have enough worker connections, so I upped that to 20,000 also. Later on, I backed that down to 10,000, which is probably a better number. And then one of the other errors that I was having was the Redis connections. So I was getting in the Laravel logs itself, I was getting, you cannot assign requested address to kind of the Redis. And then what I had to do is I had to set some network settings so that we're kind of always reusing our network connections. So by default, it was set to the number 2, which was on localhost or loopback type requests. It would reuse those connections, but globally it wouldn't reuse connections. It would always try to create another connection for every Redis connection that we needed, and that's a lot of connections going back and forth. And eventually it just consumed all the available connections, so it could not assign a requested address then. But after I changed this value to 1, so that we're always kind of reusing our connections, then all those kind of issues with Redis went away. So those are the 2 issues I had kind of doing my initial probing. Okay, so we're back in here. I just bumped this up to 400, and I'm gonna kind of probe a little bit more above and a little bit more below here, but let's go above one more time. Let's add another 100 to it, and let's see if that gets us any improvements or any degradation. And we're on a little bit bigger system here, but let's look at glances. And as we talked about before, CPU is pegged at 100%. Just kind of what happens here. You got all these PHP-FPM workers now. They're all in this running status. We set it up to that there's 500 of these things. You do have the Nginx worker processes. There should be 8 of those running, and they're definitely consuming some memory. But look at the amount of memory that we're really consuming, only 7.4%. It's kind of odd to me because, our initial computation was all based upon how much RAM there was, available RAM divided by the amount of RAM used by each PHP-FPM process. And it turns out maybe that is still pretty accurate, but it kind of feels like, how did RAM play a part? Because we're not even close to consuming, the amount of RAM that's actually on this system. All right, so our test is completed, and let's go ahead and collect our averages and put them in our spreadsheet. All right, so let's look at our results here. What we see is kind of our average response time is slowly kind of increasing. It's getting up a little bit higher, but ironically, our max response time is kind of slowly decreasing. This number here is totally dependent upon that max. And so this number is kind of slowly improving. It's getting better. It's going in the right direction, but this one's going in the wrong direction. I don't see a lot of improvements, though. What I'm going to do is I'm going to probe a little bit underneath the 323 mark. We're just kind of seeing how sensitive this is. If it's not super sensitive, then there's not a lot of value in trying to probe around this. Let's go down to 200. Yeah, just to kind of give you a visual on that optimization process. I just drew up 2 curves here. This is just a x squared curve, and this is an x to the 8th curve. And when we're doing optimization, really we're on this curve someplace. This is our current point. And then what we're trying to do is we tweak a value when we see where the next one lands. So if this is our current point and then the next one lands here, well, we know it's kind of it's sensitive enough that, we should keep heading in that direction. But if you look at the blue curve, it's kind of a flat bottom. So, if we're here and we do the next one, and this is already at 0, and then I do this one and we're at 0.0005, it's not very sensitive. So in this area, optimizing becomes kind of almost pointless. There's a wide range of values, input values that I could have here and get pretty much the same output, which is around the 0 mark. But the red curve is not like that. For that same range, which is from, maybe from minus 0.4 to 0.4, where it's flat, the red curve, I would be optimizing it and I would have some different outputs. So that's kind of our visual process that we're doing. Let's go back and see our test is completed. It has indeed. We're going to copy these numbers over. Okay, so we look at the average number and we compare it to the top line here. We have gotten a little faster. Our max has gotten a little slower. And so our metric here, that slope metric, has gotten a little bit better, or a little bit worse, I should say, yeah. It doesn't appear to be super sensitive. It's not, something where we're seeing a lot of difference between 200 and 323. Once again, I kind of feel like we've probed this instance enough to kind of get a sense for the performance that we're going to get through it. And, these are the numbers I would just run. I would run them with these numbers. So let's go ahead and mark them as the ones. And in conclusion, this T2 2XL is definitely better than the T2 Micro. Is it jumping out of the free tier better? It just depends upon how you're going to use this. So right now, this is costing about 37 cents an hour as opposed to about 1 cent an hour. Depending on the situation you're running, if you're just running a dev environment and only one developer is really hitting it, this T2 Micro is probably fine for that. I don't really see a reason to go up to the 2XL. I don't have enough data yet to say, should we go to the M7i or the C7i? That's what we're looking at next. All right, so up next, we're testing this M7i. It's the 2XL, so it's 8 CPUs again. Same amount of RAM as our T2 instance. One of the biggest differences between this M7i and this T2 is now we're starting to get some dedicated kind of bandwidth. The network bandwidth is up to 12.5 gigabits per second, and our ABS bandwidth is up to kind of 10 gigabits per second. And the T2s, those were kind of in moderate. My gut feeling, this is going to impact us a lot because we are serving up web pages over the network, and we are also pulling PHP files from the EBS volume. So let's see what the impact has here. All right, so you can see the M7i 2XL is running. It's past its instance initializing phase. I've already updated my Route 53 and I kicked off a test from Motor.io, and you can see it's already kind of running. Let's let this complete and see kind of the results that we get. All right, so this is totally completed. Let's go ahead and grab the average time, and you can already see a big difference. So even if between the T2 2XL, which has the same number of CPUs, and the M7i, if we go back to the T2 2XL, our average response time was around 13 seconds and our max was around 27 seconds. With this M7i, same number of CPUs, same amount of RAM, we're down to 4 seconds and our max is around 10 seconds. So at 3,000 requests per second, our users are waiting around 10 seconds for a response from the web. Is that acceptable? Maybe if it's a spike, right? So you get 3,000 and then if it's a spike, if it's a continuous thing, probably still not acceptable at that level. But our slope number is definitely improved. And so you can see already the impact that I think that this network bandwidth and this EBS bandwidth are really happening, because if you compare the T2 2XL and the T2 or the M7 2XL, same number of CPUs, same amount of RAM, but the biggest thing that's changed here is kind of this bandwidth on EBS and networking. The cost is a little bit more expensive. It's about 3 cents an hour more expensive. But so far, I think that performance is definitely worth the extra 3 cents. So we're gonna do the same thing we did before. We're gonna probe around 323 and see if this is flat or, if we can make this any better. And let's probe at 400 and see what we get. And I'm gonna run glances. I wanna see what this new instance looks like here. Again, expecting CPU to max out. I mean, we're starting to hit it pretty hard. It will consume as much CPU as available, which is 100%, and that's okay. This server, it's really only a web server, and all the web server processes are grabbing kind of as much CPU as it can. We're not even coming close to exhausting the amount of RAM that we have, though. And this is probably okay because, right now we're not really doing a lot of memory intensive PHP. We're not getting a lot of data from SQL. We're not kind of moving a lot of data around. That number might bump up if we ever had a request where, maybe I'm grabbing, 1,000 rows from the database. Well, now I have a bunch of data in memory, and those numbers might be different. All right, our test is completed. Just gonna refresh this. Go grab our numbers. Kind of the same thing as we saw last time. Not a lot of change here between the average response time. It was like 2 milliseconds different, 2 milliseconds faster. The max response time, it did go down, so it seems like we're kind of heading the right direction here, and our number went up. So let's go to 500, and let's see if we continue to improve. And while this test is running, I'm going to go back and look at the one we just completed. And again, one of the things you want to check is your details tab. I haven't been checking this regularly because I kind of already know. I've probed this before. I know that there's not going to be any errors here, and I don't see any 500 timeouts or network errors or 400, so we're good on that front. Let's look at our in progress test still. Okay, so it has completed. We're going to grab this number, where we're at. So it looks like our average response time went up. So we're definitely heading the wrong direction. And our max response time went up also. Going from 400 to 500 is definitely the wrong direction. So let's go the other direction. Let's see, like we did last time, and what, say, the value of, say, 200 gives us. All right, so the test is completed. Let's go ahead and grab our numbers. Let's plop them in our spreadsheet. And in this particular case, it looks like it's also gotten faster. So by a couple hundred milliseconds, our average went down, and our max is over a second faster. So I think this is definitely kind of an improvement. Let's probe a little more in this area over here on this side. We're going to go to 100. Let's see what that does for us. And while this test is running, we should just talk about being a little bit cautious about the interpretation of these results. I'm hitting one endpoint, like I talked about earlier. It's a login page. Not a lot of database query, not a lot of memory being used in that PHP request. And the results that you get may vary depending upon kind of your endpoint. So this kind of optimization, we're trying to get it to a place where we're performing as good as we can. But I don't want to get too close to an edge, because if I get too close to an edge, maybe different type of PHP requests that require more memory or anything like that might kind of push us into a realm of kind of unacceptable performance. All right, so let's grab these numbers, and you can see go from 200 to 100, we definitely got worse. Our response time was about 100 milliseconds slower. So let's probe a little bit between 200 and 323, and let's see if maybe there's something inside that window that is kind of optimal. So between 323 and 200, that's about 123. Let's divide it in half, so we're about 60. Let's go to maybe 260. Let's see what that looks like. So we have finished up. Let's copy our numbers into our spreadsheet. Let's see where we're at here. All right, so between 200 and 260, 200 is a little bit better, but we're talking 3 milliseconds better. So it's about a second better on the max. So far out of our probing, I'm going to call this row right here with the 200. That response time is the best so far, and we're going to call that the winner. Okay, the next instance we're going to test is this C7i 2XL. If we look at that instance, that is a compute optimized instance. And one of the differences that we'll see if we look at our spreadsheet, that C7i has the same number of CPUs, but it has less RAM. So instead of the 32 gig RAM, it has 16 gig of RAM. And that's probably why they're calling it compute optimized, as opposed to kind of this general purpose where we have less memory. Same amount of bandwidth. So kind of what I'm expecting intuitively, since we're not really capped on RAM with this test that we're running, I would think that these two machines will run exactly the same. So let's look at that and test that out. Because we do have less RAM, we're starting off our computation with 160 max children. I've already kind of set that up. And let's check our status here. It says initializing still. And now we should be ready to test. So we're going to kick off a test. Let's see how this one performs. Okay, so that test is completed. Let's copy our values into our spreadsheet. And this is a 0 to 3000 test again. And look at our number here. So it's about 4.3 seconds on average. When we go back to our M7i, we're about 4.3 seconds on average. So again, these two hardware configurations, CPU is exactly the same. RAM, I got less RAM, but we were never constrained by RAM. So my gut feeling is kind of correct that these are going to perform exactly the same. They have the same networking bandwidth and the same EBS bandwidth. But let's go ahead and see where we're at. So right now we're at 160. Let's take this and let's probe around that. And again, I'm not really probing on the worker process or Nginx. I just don't think that that's going to make much of a difference. I think that those impacts are pretty small for the number of requests that we're doing here. So we're just probing this max children. And let's go ahead and have it. Let's see what we get. Okay, so our test is completed. Let's grab our numbers. And we can see that our average response time has went down. That's about maybe 150 milliseconds better. And our max response time is around a couple hundred milliseconds better. So it seems like we're heading in the right direction there. That's better. Let's go ahead and see if we keep going in that direction, if that pattern holds. All right, so you can see going from 80 to 40, we definitely headed in the wrong direction on that one. So there is a minimum somewhere. Let's see if it's around somewhere between 80 and 160 still. So let's try something like there's 80 between here. So let's go up 40, maybe to 120. Let's probe there. Seeing our last test was actually at 400. Let's, we'll reflect that. So 400 here. We didn't get a 40. Let's try 120 anyways and see what that looks like. So while that's rerunning, again, the 40 result, we were trying to do 40. We actually ran 400, and 400 is definitely worse. So 400 is on the other side of 160. So we're trying something between 80 and 160. We're trying 120. Let's see what that result looks like. And while this is running, let's go ahead and look at glances. I want to see where we're at here. 100% CPU like we expected. Still, we're only using 7.4% of RAM. And again, that caveat still holds. Our PHP requests that we're doing, they're not really memory intensive. I mean, we're not grabbing data from the database and returning it and making big views or anything like that. It's pretty super simple. And so that probably is reflected here in this number. All right, so we've completed. Let's go ahead and copy our numbers in. So you can see from 160, we're at 4320. And then we went to 120, we're at 4319. And then we're at 18, it's 4287. So it's definitely decreasing in that direction. So let's go ahead and try what we originally were going to try, which is 40. Let's see what 40 really does instead of 400. Okay, so those results, you can see 40 is definitely better than 80. So we improved another 50 milliseconds here, and it definitely better here. So went from 80 to 40. Kind of feel like at some point we're not given enough PHP-FPM processes. It might be detrimental. So even though we're seeing some improvements, kind of hedging towards the number we computed was 160, but I don't want to get too far from that kind of optimal number, that formula that everyone uses. But with that said, I mean, we're just kind of probing. Let's see what we got. We'll go a little further. Go to 20. Okay, so that test is completed. Let's go ahead and copy and paste these numbers into our spreadsheet. All right, the max got better. The average got better. It feels a little disturbing that we're kind of getting down to, these numbers where we're doing kind of 20 max children for PHP-FPM when our formula said we should be around 160. Just looking back here on the M7i, the formula said 323. We tried 200, it did improve. We tried 100, it got worse. And so there was kind of this little saddle that we kind of found. Here, we're just keep getting better and better. Let's go ahead and try this one more time. Switch this to 10. Okay, so let's copy these results into our spreadsheet. And the average went down by about 13 milliseconds and improved, but the max now, it seems to have turned a corner a little bit. And now that max went up about 9 milliseconds. This number 10 feels to me like that's too few of PHP-FPM kind of children processes that are spawned up. And even though this testing results, we're getting better and better, but that's a single URL. It's not really memory intensive, and I would hedge more towards kind of bumping it back up to maybe this 120 area, which I still got some improvement. All right, but we're kind of hedging towards having a few more child processes around. So I am just going to declare this one a winner, even though technically that's probably a better response. This is probably the best of them all, had the best, at least max number. But I feel like at some point we're going to be starving for PHP-FPM children. All right, so what I'm going to do now is I'm going to run a different endpoint. I'm going to run just the home route here. So what the home route does is I pick a random lat long, and I have some random locations around the world, and I query the database for kind of the 10 closest places close to you. And so that's going to include some database queries, but I also have some other features. And so what I did is I updated this route. We're going to ramp it up from 0 to 3000 again. I have this parameter that we can enter, the database, and we're going to do that query kind of 10 times. So we're hitting the database, not just once. We're not doing that query once, but we're doing 10 of those queries. Okay, so with that said, let's go ahead and run this test. Okay, so this is running, and let's go ahead and take a look at our glances. And you can definitely see, CPU's pegged. This number, I believe, was kind of around 1 to 3 before, and now it's at 9.7. So now that we're doing this database query, definitely grabbing more memory and using more per child process. We'll just compare the response time for this as or others. Let's go and plop this into our spreadsheet. And I'm going to kind of come down a line here just so that we have some separation. So that's what we just ran, but we ran it against the slash route as opposed to the kind of the slash login route. Okay, so that's enough for this C7i instance. Let's go ahead and shut this one down. We'll switch over to the next one. Our next instance type we're going to test is the R7i 2x large. And again, it has 8 virtual CPUs. This has more RAM. So we just went from, we started off with 32 gig and then we went down to 16. Now we're up to 64 gig of RAM. The networking speed is about the same. So because we weren't really RAM bound at all, I don't really expect there's going to be much difference between these instances for our test case. Now, if you were doing a lot of queries where every PHP process was going to grab, hundreds of megabytes of data from a database, then I think you're going to have to adjust depending upon, which of these 3 instances you really want. Obviously, the T2 micro isn't as performant as these instances are, mostly because of the networking bandwidth and the EBS bandwidth, but you still have to kind of choose between how much RAM that you're going to need. So with that said, let's go ahead and take a look at this. I've already switched over to the instance, so I have this R7i2XL. Let's just make sure one more time. R7i2XL, that's the one we want. And let's do a quick status check. Everything's good to go. So I've already set up the Route 53. We should be good to go with that. I've adjusted our test so that our test now is back on the login page. And I think we're ready to kick off a test. Let's go ahead and run this. Okay, so that test is completed. Let's go ahead and copy in our data. So we are in the R7i2XL. All right, just off the bat comparison. So we have 651 max, kind of the PHP-FPM processes. If we compare between these last three instances, so we're getting about 4.6 seconds average response time. Here we're getting about 4.3. It's in the same range. Here we're getting about 4.2. That's kind of all in the same range. So we're just going to explore this space a little bit and see if we can optimize this. I'm going to go ahead and bump this up to, let's say, 800 just to see what that gives us. And again, if we just go back to our instances that we're testing, I'm really not expecting a lot of difference between these. These are all kind of that 7th generation kind of hardware that Amazon has. It's all using the Intel processors. They all have 8 virtual CPUs. They all have the same kind of network bandwidth and the same EBS bandwidth. And the only real difference we're talking about is how much RAM is on these systems. And because we're not doing anything where we're pushing the limits of that RAM, all three of these are going to be about the same performance. All right, so that test is completed. Let's copy in what we have. So the average time went up just slightly, like around 70 milliseconds, and the max time went down about 200 milliseconds. All right, so it looks like this is where that minimum is. And we saw the same results kind of over here where we started chasing this down, and we had about 10 was our kind of minimum on our test. And at that time, I kind of hedged back up towards something between what the formula says and what we kind of expect. Wasn't really expecting it to go that low. Same thing here. I don't feel quite comfortable putting this number of max children. I feel like at some point you're going to need more PHP-FPM workers to handle kind of the requests. And so even though this is our best performance, I'm hedging back up towards our 650, maybe somewhere kind of happy medium around 500 where we just broke the 10. So I'm going to call this kind of the winner just based upon kind of intuition and what I think. Yeah, I'm losing about 300 milliseconds of average response time, but I think in the end, having that many kind of child processes around is probably going to be best for your application. The last instance type we're going to test here is i4i, and again, 8 CPUs. I might scale up a little more and see what 16 CPUs or 32 CPUs looks like, but this is the last kind of across the instance types that I'm going to do. This one is 8 CPU. It has that 64 gig of RAM, has kind of the same networking and EBS bandwidth. The one difference that I did notice, and I'm not sure this will come into play, was this is a storage optimized solution. And so this i4-2XL is right here, and it has this SSD storage on there. So I don't know if that's kind of where our EBS volume is going to be. If it is, this should be a little quicker because of kind of the file I/O time. It should be pretty fast, but we'll see. My gut feeling is it is not going to matter because it also lists this up to 10 gigabits per second. So let's do the test and we'll figure that out. So our instances, I've already kind of switched it over. It says it's still initializing, and we'll just give that a couple of minutes here. In the meantime, I have already kind of set us up so that we're running our initial set point, which is 651. So we go over here, 651. The test is going to be a 0 to 3000 test, and we're going to measure our responses. All right, so we're all set to and let's go ahead and kick off that first test. Okay, so it looks like that test is completed, and let's go ahead and copy in our results. These seem a little slower than the previous one. We'll compare that in a second. But I thought that we were around 10 seconds before. Now we're in 11 seconds max. All right, so this is the test we just did, 651 against the R7i. That's 4.6 versus 5.0, so that feels like significantly slower. 10.7 versus 11.0, again, slower. With hindsight of this kind of being optimized on the lower side, let's go ahead and start to go in that direction. Okay, so these results are very similar to our R7i instance, and I'm not going to explore this one any further. I'm kind of thought that because it was storage optimized, it had that SSD, that maybe our code would be put on that, but I don't think it is. So this instance isn't really providing us any more benefits. So I'm not going to explore this one anymore. Okay, so we've kind of done phase one of this testing, which I wanted to kind of test initially the same number of virtual CPUs, 8, across different instance types, whether they're kind of storage optimized or memory optimized or compute optimized, and see kind of what the performance is. And under the summary tab, we can see kind of the best results from all those cases. So we tested all of these cases. This T2 Micro really isn't kind of a fair play because this really only has one virtual CPU, but I put it in the chart just so we can see. This T2 XL, this wasn't, even though this had 8 virtual CPUs, the bandwidth and the network and EBS just wasn't sufficient really to kind of offer the same performance levels. So then we tested these M7i, C7i, R7i series, and even the i4i series. And these really all kind of ran the same kind of Intel infrastructure. They all had 8 virtual CPUs, and the biggest difference here was between the amount of RAM. So the C7i was compute optimized, which means that it had kind of more CPU than RAM. It only had 16 gig of RAM. The M7i was a kind of a general purpose one. It had 32 gig of RAM, and then the R7i had 64 gig of RAM. But if you look at the performance just graphically, there's not much difference between all of these. Price-wise, the C7i, because you had less RAM, is a little less expensive. And so based upon that, what I'm going to do is I'm going to take that instance type and we're going to test that one further. And here's my test cases. So the C7i kind of instance family, which is compute optimized, now we're going to scale from 2 to 4 to 8 to 16 to 32 processors, CPUs. And along with that comes whatever memory that it has. The bandwidth is kind of the same, except for when we get to the last one. The last one, it doesn't say up to 12.5, it just says 12.5. So maybe the bandwidth is guaranteed in this last one. But we'll kind of test these out and see what we get. That's the plan for phase 2. Now we actually are doing the vertical scaling. Let's just see kind of the results as we kind of scale up the number of CPUs and RAM at the same time using the same instance type. Okay, so our first instance that we're going to look at is this C7i large. It has 2 CPUs. Remember before we had 8. This is the one we tested previously, 8. And we only got like 4 gig of RAM. I've already set this up and we have our sheets up here. We're going to put our numbers in, same thing as we did before. We're already running this C7i large instance and it's ready to be tested. I've updated Nginx Comp, so it has 2 worker processes, and I've updated PHP-FPM Comp, so we got 37 max children. With that said, let's go ahead and kick off this test and let's see what results we get. Okay, so that test has completed. Let's go ahead and grab these test results, the average. And we can see already our numbers are a lot different. I mean, with only 2 CPUs, we're really bound by the CPU in this case. So if we go back to our C7i instance, we were around 4.3 seconds as our average response. And now we are in the 11.5 seconds. So that change from 37 to 20 did improve the situation a little bit, but we're still in the ballpark of 11.3 seconds on average response time. I don't feel like we're going to squeeze much more juice from this lemon. So if we fiddle around here, we're just not probably going to get much better than these numbers here. So let's move on to a different instance. We're going to move up to this C7i XL. All right, next up in our scaling up adventure here, we get the XL. So the C7i extra large costs about 17 or 18 cents per hour. I got 4 CPUs and about 8 gig of memory. I've already adjusted our instance so that we're running about 78 children, and I got my tab here. So we have 78 max children and 4 Nginx processors going. Let's see what our instance status is. It's still initializing. We'll just give that a couple more minutes. Okay, so now we're at 2 out of 2 pass. So everything's good to go and we're ready to do a test. Let's go and kick off our first test here. So this is improvement over the just large version, which had just 2 CPUs. You can see it's roughly half. So we were around 11.5 and now we're down to 6.3. So a little bit less than half, I guess. But compared to the 2XL, which has 8 CPUs, we're still not quite there. So we'll be able to compare all those in a little bit. Let's just focus in on this one a little bit more. Let's run it one more time. So maybe 39 or 40. Let's put 40 in there. It's an easy number to get. Okay, so definitely made a little bit of improvement and the max got a little worse. So again, I'm going to not chase this. I think we're in the ballpark of what this instance is going to perform like, and we're just not going to be able to squeeze much more from this lemon either. So we're just going to leave this the way it is, and we're going to bump up to the 4XL. If you remember, we already did the 2XL. So that's the previous one here, which was the 2XL. Now we're going to bump up to the 4XL. Okay, so we're all set up for this 4XL. We got 16 worker processes for Nginx. We got 324 max children for PHP-FPM. Check on the instance here. The instance is, again, it's the 4XL, and our status is we're good to go. So let's go ahead and run a first test. Okay, so that test is completed. Now, this is interesting because we got our max and our min, but you can see the shape of our curve. At about this point right here, something happened. And something happened in such a way that it impacted kind of the slope of the curve here. And if we look at our details, we can see over our details what happened is we stopped getting kind of HTTP 200 responses or successful responses, and we started getting these 500 responses. So we need to investigate why that is. So the first thing I'm going to do is I'm going to look at the Nginx logs, because that's the very first service that our request response hits. And we're going to tail out, say, the last 1,000 lines of Nginx logs, which are at var log Nginx error. You'll see them here. That is very odd. First of all, it's odd that I'm not getting more lines. Let's see, so the error logs, you can see there's a .1. It just turned over to another new error log here. So there's a lot of errors that just happen. Let's go ahead and look and see .1. Okay, so I think this is probably our issue, is worker connections are not enough. 1024, when is the date on this? 6/2, that is not our issue. So all of these errors, these happened a couple of days ago. These errors happened just now, but I don't think it's going to be this many. There's not that many there. But what is this? Access forbidden rule on /.env. I think what this is somebody external. So somebody external is trying to get our .env file, and it's saying access was forbidden, so it's protecting us. I don't think these errors are associated with what we're seeing there. So let's go a little bit further. Let's go look at our PHP-FPM logs. Let's see what we get here. And the date is right. I'm not really noticing any errors here, so I don't think that this is kind of our application level errors. I don't think it's happening there. Let's go look at our Laravel logs. Now we're starting to maybe get someplace. Let's see what we have. The timestamp on this top one, 6.3 error, cannot assign remote address. This looks to me like it is that Redis exception. And I shared this in previous parts where I had fixed this at one point by modifying a setting. So cannot assign a request address
So what I did is I set up the network so the TCP connections are reusable. I want to double check that and make sure that that is the same. So I'm just going to slide this down a little bit, and I'm going to get out of this session here I'm in is our demo_1 deployment user. Doesn't really have a lot of access to anything, so let's go ahead and get out of there. And I want to run this to see what that's set at. And it's set at 2 again. So this number, apparently when I changed instance types, this number got set back to 2. And if I set this to 1, I should be able to fix this. And I think if I recall, if I look at it again, it's set to 1. Okay, so that should take care of that. Let's rerun this test. I don't think I have to restart anything. Let's rerun it and see what we get. Okay, so I'm glad that we ran into that issue, because I think that that's useful when you see those kind of changes in your curve. That's your time to go investigate things. I refresh this. Let me grab these numbers here. Let's put them in our spreadsheet. Okay. Again, we'll play with this a little bit, but I don't think we're going to get much more performance from here. But let's go ahead and maybe drop this to, say, half of it, 150. Just see what that gives us. It is interesting how that TCP value got reset. I'm not sure how Amazon does it when you go change instance type. So you go from, say, a T2 micro to a T2 2XL. It seems like all of our code is there. It seemed like all of our PHP configurations there, all the Nginx conf is there, and the values that we had changed just recently were transferred right over. But this particular setting is maybe deep enough where it has to go and grab it from somewhere else. So there may be different kind of layers, like in Docker or something, and there's some lower layer that had that TCP connection. Be interesting. I think next time we switch to a different instance, I'm going to go double check that one more time just to see if that holds. But here we are one more time. Let's get the results. And again, I'm not going to chase this much further. It looks like it improved it maybe 100, maybe 30 milliseconds, 40 milliseconds or so. So we're kind of seeing the amount of performance that we're getting from these 16 cores. So we got one more size to test, and let's go ahead and get that next. Okay, so I've kind of reselected this size. I'm running into this issue right now, where it says that availability zone has insufficient capacity. And what I've read about this is that means that there's just not enough kind of resources for me to start this size of instance up. And I can retry this, maybe wait a couple minutes and retry it, but I've been waiting for about 5 minutes, and I'm not sure that I'm going to get this thing to be able to start. Scratch that. Okay, so I was able to successfully start it. And now we just have to kind of go through our process. We wait for this. While that's initializing, let's just go and look at our comparison here on cost. We can see that the costs, as we're starting to scale up, obviously it's costing us more. This new version here, which is 8XL, it's got 32 cores, or it's got 32 virtual CPUs, I should say, and then about 64 gig of RAM. This has cost us $1.42 per hour. So that's quite a bit more than, even if you just scale it back down to kind of this 8 or 9 cents an hour. So even if it's 10 cents an hour, that's a lot less than $1.42. But if your application's at a point where it demands that amount of scale, then you probably can afford it, especially if you're monetizing it correctly. You can afford to run, this large instance. The other thing I'm interested about here is, all the instances so far have said up to 12.5 gigabits per second for the network bandwidth and up to 10 gigabits per second for EBS bandwidth. This, it's just locked in at 12.5 and 10. So I wonder if that makes a difference too, but we'll see. All right, so we're going to go back over here. Now it's all ready to go, not initializing anymore, and let's go ahead and run our first test. So as this test is moving along, obviously these little blips here are kind of interesting. Maybe in a bad way. We're gonna have to look at the details in a little bit second, but you can see another little blip here. So every once in a while, it looks like the response times goes up to above 5 seconds. But here's kind of that trend that we probably would have seen if those blips weren't there. So let's look at our details. And I'm not seeing much. I'm not seeing any errors. I'm not seeing 500 errors, 400 errors, timeouts. Let's go ahead and get some of this off there. So I'm going to get the success. We'll move that. Total responses, we'll remove that. Yeah, I see no errors. That's interesting. But because we have these little blips, I want to go look at our logs and just see if we see anything new in there. So we should be able to tail our Nginx log first of all. And these are the issues that we saw the last time. So someone's trying to get to our .env file. So we're not going to look at that. That's not an issue. Let's tail our PHP-FPM logs. And again, I'm not seeing much here. Okay, so let's jump into our deployment user. Go look at our application logs. And I didn't see the timestamp. We'll have to go back and look at the video, but this kind of feels 1923. Yeah, this feels like this is old. So this is at least 20 minutes ago. So I think that this is not anything new. All right, so given that I can't find any errors, let's go ahead and take these numbers into our spreadsheet. This max is a little suspect because, it spikes up to here and our max is probably up there. But in reality, if you were to draw this line and continue it out, if it didn't have those spikes, that max would be around 1851. That's kind of where it probably would be. But we're going to put the 6739 in just to keep the thing honest. But if this was around 1831, that's really kind of the number that we're really kind of feeling, it looks like. So I'm not going to do anything different. I'm just going to rerun this test and see if we get these same spikes. And while we're running this time, we'll get out of our demo user and we'll run glances. I want to see if there's anything going on here. So memory, we're 100% CPU, expect that. 6.2%, we're good here. All right, so we got another one of those little spikes. It was spiked up to around 500. I didn't see what was happening during that spiking period. I think what I'm going to do is, after this completes, I'm going to pause this video and I'm going to scrub back and I want to see at this time what was going on when this thing spiked, if there's any processes that happened, and we'll see if we can troubleshoot this a little bit further. But unfortunately, I can't bring you along with me if I have to kind of stop this. No, that's not true. I can stop this and we can do that anyway. So I'm going to go ahead and stop the recording here. Okay, so now we're recording again. I can't really tell anymore, but anyways, we are recording again. I'm just going to get this image of me out of there, and what we're going to do is we're going to scrub to the end of this video. Okay, so we're kind of scrubbing back and forth. You can see here the 100% CPU usage, and then all of a sudden we hit a period where we start to drop down from the 100%. And we're not running 100% anymore, but system D resolved is running, and that's taken up about 30%, and that looks like it's as much as the CPU. So at some point it kind of feels like something stops processing and we're waiting for, something like there's file locks or some thread locking or something going on, and once we get past that, On the other side, the CPU ramps back up and we get back in our groove again. So we're back at 100%. And then let's see around our second spike. Again, I can see the system D resolved happening there, and that's ramping up, and our CPU is dropping to 2.2%. This is where our spike comes in. Right there, you can see the spike happening. System D resolved. Okay, so that culprit, I wonder what that is. Okay, so let's go ahead and get rid of this file. I don't think we need this file right now. And I want to look at that systemd resolve a little bit deeper. I wonder if there's a log file for that. So that service that I suspect is happening is, let's see, this service here, systemd resolve D. Let's look at the status of this. This is a network name resolution. So it's a DNS resolution service. It's actively running right now. Let's go and see if we can see anything about this in maybe the log file. Oops. So we're going to tail out, we might need sudo on this one, tail out, say the last 1,000 lines of probably maybe the syslog. Let's try that. And these are all from June 3rd, and this is around kind of our time, it looks like it. Okay, so just looking at this log, I'm not really seeing much in here at all. Okay, so after some investigation, I have not been able to figure out what the root cause of this is. I suspect it's something related to that systemd -resolve D daemon that's running for kind of network resolution, because I see that spike up that comes up here, and then the CPU usage goes down kind of low or around just the usage for that daemon, and then all of a sudden the thing gets back to work. Regardless, what I'm going to try to do is I'm going to adjust our values, and maybe there's something with having this many children. And we're just going to go ahead and have this. We're going to bring this down to about 300 and see if that maybe fixes the issue. I doubt it. I don't know why they would be related like that. But let's go ahead and give that a try. All right, we'll restart PHP-FPM. We should be good to go. And let's go and kick off another test here. All in all, I mean, this server is definitely faster. You can see the average response time is way faster than the other instances that we've seen so far. Yeah, it looks like we're getting another spike here. So if you ignore these spikes that happen for some unknown reason, if anybody knows why this is, let me know. But during this kind of little small window, it's like a 5-second response time. And they're definitely at regular intervals too. I mean, this spike is around 16 to 17 seconds, and this one is, say, 35. So 16, so 35 minus 16, what is that? So we're saying it's every 19 seconds. So if I add 19 to 35, I'm predicting this should be at about 54 seconds, and there it is, around 53, 54. So it's definitely at a kind of a regular interval time-wise. But if we copy in our numbers, we're seeing not much improvement. But again, this is the number. If you could get rid of those kind of spikes, why those spikes are happening, I don't know. All right, so let's kind of conclude what we saw from scaling up. So here's our C7i instance. Again, we went from large XL to 2XL to 4XL, 8XL, and then I have this other 8XL here. And we'll talk about that last row in just a moment. But the difference is you can definitely see as you scale up the number of CPUs, you get more RAM, but you're also paying more for that kind of EC2 instance. The bandwidth and the networking was all the same except for when we reached the end here. You know, this had kind of some guaranteed 12.5 and 10. These were, it said kind of up to, I'm not really sure what that means, but anyways, our average response time, these results are, you know, from all of these, you can see kind of it's increasing in performance. So the bar height represents kind of the response time. So for just a large, which 2 CPUs, our average response time was around 11.3 seconds. If you double the CPUs, you get about 6.4 seconds. If you double it again, you get about 4.2 seconds. And if you double it one more time, you're down 2 seconds. And if you double it again, you're about 1.2 seconds. Now the last one, if you recall, we had our test results had these kind of spikes in there. I'm not sure what the root cause of those spikes are. So at some point, I just kind of gave up on that. But if you understand what those spikes are, go ahead and share in the comments below. But generally, this is a triangle, and its max value is about 1844 over there. So the average of a triangle is about half. So we should be really about 916. And that's what this one is here. It represents kind of the ones without that, kind of those spikes in there. Okay, so that kind of wraps up long day of testing. So I've kind of run through different instance types, and then also we scaled up through one instance type, so increasing from like 2 virtual CPUs all the way up to 32 virtual CPUs. And along the way, we've had some kind of troubleshooting, some issues we ran into, some errors, like 500 errors, and we had to kind of dig into those. But it's been interesting overall, and kind of what we expected. If we want to scale this up vertically, we certainly can do that. When we go back and we look at some of our response times, this is linear, like what we thought it was going to be. And, as we increased the number of requests per second, we knew it was going to take longer. So each of those processes would, they would kind of compete for resources, and it would just take longer for the CPU or the computer to respond. The interesting point that I saw was even in the T2 Micro, those responses always came. At 3,000 requests per second, I wouldn't want my user to have to wait for what was like the 55, 56 seconds or something like that. I would not want them to have to wait that long. But what's interesting for me is that that process was resilient enough that it always did kind of respond. Now, obviously, there's a timeout that's pretty close to, I think, 60 seconds. You could adjust that timeout so that maybe you extend it a little bit. I forget which one, if it's PHP-FPM or Nginx. But obviously, we wouldn't want them to hit that timeout. And the other thing that we saw was, as we started to scale this up, this is maybe the average response time, so 6.3 seconds. And that average was kind of related to our max. So we maxed up to 3,000 requests per second. If our server is only handling, a couple hundred requests per second, this server is going to respond fine. Probably this one's going to respond fine. You really have to kind of look and see what your load is really going to be like on your server. One key aspect of providing an architectural solution is we want to understand the cost impact. And there's no reason for me to scale above maybe a C7i large if my average user, they're going to get their pages on time, and it's less than sub-second, and this will be able to handle up to 3,000 requests per second in a spike, and that user would have to wait maybe 20 seconds for that response. And that depends upon your application, right? So if your average load, on a day-by-day basis is your couple hundred requests per second, this is probably okay. You're gonna pay maybe 8 or 9 cents an hour, and this computer or this instance is probably perfectly fine for you. The other thing that we learned is Amazon makes this really easy for you to scale this up. Unfortunately, you do have to kind of shut your instance down. You have to stop it, and then you can change the instance type. And there are ways to kind of hot swap those. What you can do is you can stand up another instance, exactly the same type, but maybe you're doubling the CPU. And then what you can do is you can use DNS to switch between the old, smaller instance to kind of the larger, newer instance. And once you pass kind of that TTL for the DNS route, then you can shut the smaller instance down. But once we start looking at horizontal scaling, there's even easier ways to be able to incorporate new EC2 instances into the mix. And that's what's going to come up in future videos. So the next video, we're going to start talking about horizontal scaling. So if you made it this far, I appreciate you. This is a long video, so there's a lot of data in here. I actually shot this a number of different times. I was probing these instances, trying to figure out what the best tests were. This is kind of where I landed. Hopefully that this data is useful for you and is interesting. If you like content like this, hit that like button and subscribe. We'll see you next time.